Okay. All of you have heard of an acid, but some of you might not have heard of a base. You've probably heard of alkaline. Alkaline's kind of the old world name for a basic solution. Now, when I say basic, I'm not talking about simple. I'm talking about a specific chemical phenomenon that happens with basic chemicals. And you'll study these in acids at length in your next chemistry class as well. It's a huge topic. Okay, so what is an acid? Okay, everyone's heard of an acid, but probably you'd be hard pressed to define what is an acid. Okay, an acid is a compound that disassociates a hydrogen ion, H plus, or that's also called a proton. Now, so if a compound has an H in it, like this guy here, it has a possibility of being an acid. But it's an acid only, no exceptions, only if it disassociates H plus or a proton. Now I'm saying proton because in OChem, they don't talk about H pluses, they talk about protons. So I want you to get used to using those terms interchangeably. Okay, and there are two kinds of acids, strong and weak. Most acids are weak, millions of acids in the world, particularly on the biochemistry side. Lots and lots and lots of biochemical weak acids. Okay, now what's the difference between a strong and a weak acid? The big difference is that strong acids disassociate the H plus 100% of the time. There are 7 of those in the world, only 7. The ones that you're going to be exposed to in this class and your next chemistry class are 3. There's hydrochloric acid or muriatic acid, the kind you use in pools. Nitric acid, also called printer's acid, because in the old days when they used to use lead type, they used to use nitric acid to clean up the area, and then also sulfuric acid. Those are the 3 most common acids you're going to run into that are strong. Now, you've probably run into a weak acid when cooking. Who can think of a weak acid that's used in cooking? Yeah, vinegar, acetic acid. Very, very common cooking acid. It's also 5%. All commercial vinegars are at 5%. If it's not at 5% when they make it at 5%. They either dilute it or concentrate it to 5%. That includes apple cider vinegar, which I love. I love the taste of that. Or distilled vinegar, which is the only thing in that is pure vinegar, nothing else. But acetic acid is a weak acid. It's the most common weak acid. But, there's citric acid, there's vitamin C. There's a whole bunch of weak acids out there, millions of them. In fact, there is when you get into biochemistry and carbohydrate metabolism, the first stage of a carbohydrate metabolism of glucose is called glycolysis. And the first thing it does is it takes glucose and puts a phosphate group on it. Phosphate is another common weak acid, by the way. It's used a lot biochemically. It's not used a lot in cooking, if at all, but it's used a lot in biochemistry. Your DNA, your RNA, your proteins, all of them has phosphoric acid groups embedded in there. Okay, so if a strong acid disassociates 100%, that means weak acids dissociate less than 100%. Greater than 0, less than 100. So that's what these arrows mean. Notice up here we have a big giant arrow. One direction only. With weak acids, there are two arrows. A little arrow and a big arrow. The little arrow means a little bit disassociates. In fact, that's what acetic acid looks like, by the way. And acetic acid has 4 hydrogens. So which one comes off? It's the one next to the oxygens come off. Now, what determines which one comes off? And like I always say in this class, it's stability. Of the possibilities of all the hydrogens coming off, that's the most stable of the group. So there are 4 variations, 4 hydrogens, each one can come off, but only one of them comes off to create a stable product. Okay. Now, we have a compound like ethanol, that's drinking alcohol, C2H4OH. Actually, that's not right. C2H5OH. You know, I teach this stuff, you'd think I'd know. Okay, so ethanol, it's got 6 H's, then it might be an acid. So the question is, one, which H could potentially come off? There are 6 of them. The way ethanol is written like that is because one of the H's is attached to the oxygen. That means the other 5 are equivalent H's. So the possibility exists that that H that's attached to the oxygen, just like acetic acid attached to the oxygen, it doesn't come off though, because what it makes is very unstable. Remember, stability is the deal. If it doesn't make something stable, it's not going to come off. You have a question? Weak. If it comes off, it's an acid. Question is it strong or weak? If in doubt, always say weak, because there's only a few strongs. If it's strong, all of it comes off. If it's weak, only some of them come off. And it depends on which weak acid you're talking about. Like with citric acid, that has 3 hydrogens that can come off. Phosphoric acid has 3 also. Acetic acid only has 1 that can come off. But they always come off a little bit, as opposed to strong acid, which they all come off. Does it matter? It stays on. What makes it weak is some of them come off. The key word is some, not 100%. So some of them come off, not all of them. Strong acid, all of them come off. Because I've been teaching this for 35 years. And you can't look at it a priori and say, oh, this is going to come. Right. Now, one key thing, and I'm not trying to, when I said 35 years, I just, right. The one thing with organic acids is the COOH. So you asked me, looking at it, can you tell? If it's got a COOH, that'll come off. That's about the only one that I can say. Because it doesn't come off 100%. Comes off probably. I can, because there's only 7 strong acids in the world. Yeah, and three of them we work with, all the time. That's sulfuric, nitric, and hydrochloric. Those we work with all the time. So if it's not one of those three, then it's weak. So basically, huh? Three are, I think I even listed them here. So sulfuric is H2SO4, nitric is HNO3, hydrochloric is HCl. And there are four more that they're kind of unique. You wouldn't run into them very often, especially in a freshman chemistry class. Okay. Now, the opposite of an acid is a base. Now, what a base does, it's similar to an acid, only it instead of H plus, it gives off OH minus. And that's called a hydroxide ion. So there's H plus, OH minus, opposites. Okay, so we have strong bases, weak bases, and no bases, just like with acids. Strong bases that are only two that you need to work with here. And the common name for sodium hydroxide is lye. All of you have probably heard of lye. That's NaOH. Now, lye has an interesting property around fats. Fats are normally something called triglycerides. Triglycerides around lye makes soap. So who has heard of ivory soap? Gosh, everyone's raising their hand, right? That's lye soap, made from lye. In organic, at least in my organic classes, you make soap. We take a fat with strong lye, we make soap. And it's very easy to do. Yeah. It'd be in 2B. Yeah, in my 2B class, you make soap. I don't know about, huh? Sexity. And that sexity is 306. Yeah, it's just it's called transesterification or saponification. There's a bunch of funny words for it. But basically what I'm saying though is when you get a fat around a base, it goes through this reaction. Now, when you clean your kitchen, particularly around the stove, in fact, I was doing that last night on my stove, and I was noticing that a lot of my my microwave is above my stove where I fry stuff. Frying stuff frequently will kick off little splatters of grease because you've got water based in your food, which boils and then splatters up. And then I started going like, it's sticky. That means there's, so I had two options on cleaning. I could use hot soapy water, or I could use something with ammonia in it. Now, ammonia NH3 plus water forms ammonium hydroxide. Ammonium hydroxide. That means it's a base. So what happens is when I spray ammonium hydroxide on my greasy spots on my microwave, I convert it to soap. And then it wipes right off. So when you have a kitchen spray cleaner, make sure it's got ammonia in it. If you're cleaning glass, make sure it doesn't have ammonia in it. Because glass spots are usually a salt of some kind. So glass cleaner, it's got usually alcohol in it and some other things, which doesn't clean grease very well. So there's two cleaners in your kitchen, one for glass, one for grease. Now you can make your own cleaning stuff really easily. You buy Parsons concentrated ammonia cleaner. It's like $3 for a bottle like this, and you dilute it in your spray bottle. It works great, extremely cheap. So basically, you can make an ammonia cleaner for like a quarter. Works just as well when you buy it pre-mix. And the typical brand, and I buy it at Raley's all the time, it also works as a great bug killer. Because my apartment complex has an occasional roach or 12. And man, you spray them and they turn over. They do not like ammonia. Also, gnats, none of them like ammonia. So it's, and what's cool about it is to make ammonium hydroxide is you take water and you bubble ammonia gas through it. And the gas forms NH4OH, which is ammonium hydroxide. Now, the cool thing about using ammonium hydroxide as a pest spray, you can spray it anywhere. Because what happens is it's a gas dissolved in water. So as it evaporates, the gas leaves, and what are you left with? Water. No residue whatsoever. So it's great to spray around foods and all that stuff after it's evaporated. If you do it too early, it tastes awful. Yeah. Huh?
Is it safer on pets?
Yeah. Yeah. I have 3 dogs, and they eat everything off the floor. There's something else I was going to say too. That's what happens when you're 75. Yeah, the brand is Parsons on the ammonia. What was I going to say? I get very frustrated when I forget my train of thought. Tonight around midnight, I'll go, oh yeah, that's what it was. I think when you're talking to your grandfather and he says the story over like 10 times, you keep saying, Grandpa, you've told me that already. My daughter always says that. And I tell my daughter, live with it. You'll be here sometime too. So anyway, okay, so okay, so these are the 2 strong bases, sodium and potassium hydroxide. And lye, a lot of farmers used to have lye pits. So whenever they get anything dead, they throw it in the lye pit, and the lye would dissolve all the tissue. You'd just be left with bones. I don't know if farmers do that anymore. I had a ranch in Winters. I had a walnut ranch. We didn't have any animals, so I didn't have a lye pit. But I don't know if they have lye pits anymore in farms. Okay. Now I want to show you a very interesting compound. This compound here. You've probably heard of it. Water has an H in it and an OH in it. So what happens with water, it disassociates the H plus and it disassociates the OH minus. So water is both an acid and a base at the same time. And it's extremely stable. So Water then, notice we have the little arrow and the big arrow. That means it's weak. Most of it stays as H2O, but we also have H plus and OH minus. Now, that is the driving force for many, many, many reactions. Biochemically, organically, inorganically, formation of water. Because water is so stable. So if you can form water from your reaction, it'll happen. Okay, so how do we measure acidity? And all of you have probably heard of pH. And when you get into your next chemistry class, you're going to be calculating pH. I'm not allowed to teach pH in this class, how to calculate it. And the definition is it's the negative logarithm of the hydrogen ion concentration. So you use your log function on your calculator, all that stuff. But pH 7 is considered neutral. Anything below pH 7 is considered acidic. Anything above pH 7 is considered alkaline or basic. Now, drinking water is a real problem, making sure that your drinking water is not acidic. Because if your drinking water is acidic, the acid in the water will leach out stuff in your pipes. And if your pipes are old, you probably have something called a lead gooseneck attaching your city water or your well water to your house. That lead gooseneck has lead metal in it. Lead metal in an acidic environment will leach out the lead into the water. Think Flint, Michigan. So, a good friend of mine is a geologist, and he specializes in water-related stuff. And you would not believe the crap in our water. Do you know there's arsenic in our water? Arsenic. Now, arsenic is a really good poison because it binds with an amino acid cysteine, which messes up enzymes and stuff. Arsenic. You know what they treat chicken breasts to keep them pink? Arsenic. Yeah. It's not nice. And this country has a pretty good potable water system that's public. Can you imagine a poor country? Who's heard of the book Silent Spring? Anyone? Yeah, it's a pretty old book. And how about Erin Brockovich, the movie? Yeah, same thing. Another good book to read is called The Jungle by Sinclair Lewis. It's about the meatpacking industry in Chicago at the turn of the century, last century. Wild, incredibly wild stuff that went on. It's all I can say, it's incredible in a bad way. Okay, so pH is the metric we're going to use for whether something's acidic or alkaline or basic. Now, the goal on public potable water, potable means drinkable, is to keep it around 7.03 pH. Barely basic. Now, up in Tacoma, a lot of the water was acidic. And I had a friend with an old house, and I go, John, you need to redo your pipes coming in from the street. He says, well, they works fine. Explained to him about lead goosenecks and all this stuff. And Tacoma's water is acidic. And by the way, he didn't do it. Did not follow my advice. Okay. Now, there's something called a neutralization reaction. That's when we have an acid and a base. When we put those two together, we form water plus a salt. And when I say salt, that's what's left over after you take out the H and you take out the OH. Whatever left over is called a salt. And that salt is a cation plus an anion. So in lab, we're using an acidic compound called potassium phthalate, potassium hydrogen phthalate, KHP. That's a solid acid, weak acid too, by the way. And we're merging that with sodium hydroxide. So now we're getting water. We're getting an H off the KHP. So the H in the middle is the one that leaves, bonding with the OH from the sodium hydroxide forming water. Now this is a classic neutralization reaction. I have taught this lab at least 100 times, if not more. It's done in every single chemistry class, inorganic chemistry class. It's just classic. And the reason why we use a dry acid, KHP, instead of a wet acid like hydrochloric acid or something, which is a liquid, we can measure much more precisely dry stuff than volumes of liquid. That's why they always used a dry acid, KHP. And interestingly, they stopped making it. So I don't know what schools are going to do when they can't get KHP. Okay, so let's look at a problem involving acids and bases. Okay, if 20 mils of an unknown acid is titrated with a 0.134 molar sodium hydroxide, what's the concentration of the unknown acid? And this is basically lab 16. We're doing lab 15 today. Okay, so what do we know here? Okay, first of all, we know that we have an acid and a base forming a neutralization reaction. So we have okay. Now, if this was a balanced equation, the coefficients would be 1, 1, 1, 1. Now, sometimes with acids, more than one H could come off. Sometimes 3 H's could come off. Like citric acid and phosphoric acid, both have 3 hydrogens that come off. In our class, we're only working with 1 hydrogen coming off. Only 1. You're going to immediately get into 1A and 2A, and you have 2 coming off and 1 coming off, just a variety. But I'm going to focus on just 1 coming off. So that means 1 mole of acid plus 1 mole of base gives us 1 mole of water. Okay. Balanced equation. Unit 4 stuff. Now, yesterday I mentioned a reaction or a calculation on calculating the number of moles. So we have concentration in moles per liter times liters equals moles. So over here, we have a mole of acids. That means that we have a concentration of acid times volume of acid equals mole. So this is, again, the acid part. Concentration of base times liters of base equals mole. And that's going to yield a mole of water. Everyone okay so far? Okay, so we look at a titration. Now, how many variables are down here? Bottom here. Got 4. We've got the concentration of the acid, volume of the acid, concentration of the base, that's 3, volume of the base, 4 variables. To solve an equation with 4 variables, how many do we need to fill in to solve that for one of the variables? 3. 3 of the 4. Okay, so let's go back up to the titration problem. Okay, we've got volume of the acid in milliliters. Got to convert it to liters. Okay, so that's going to be, do we know the concentration of the unknown acid? No, that's what we're trying to find out. So we're going to leave that as moles per liter. Do we know the concentration of the base? That's 134. Now that's your goal today in lab 15 is to find the concentration of the base, which is 0.1 something. And you know the volume of the base. It's okay, the initial reading on the burette was 2.34. It ended up turning the indicator pink. So what is that? That's what is it? Convert that to liters. So it's going to be I'm just going to say acid for the unknown concentration. Now, at perfect neutralization, it's a 1-to-1 correspondence. I'm not talking about excess base or excess acid when it's perfectly neutralized. That means those are equal. Only at perfect neutralization. Now, when we titrate, we can't tell by looking at it when it's neutral. So we have to put a chemical in there called an indicator to tell us when it's perfectly neutralized. That's called an indicator. It indicates neutrality. So starting off with acidic conditions, the indicator is colorless. When it goes basic, it turns pink, Barbie pink. And if everyone would look back in the far back row, far left, that's what Barbie pink looks like. It's perfect for Barbie pink. Okay, when that happens, this equation is valid only when that happens at neutrality. So now we have an unknown acid concentration times the volume equals base concentration times volume. We just solved now for this guy here. Now, whenever we talk about concentration, we can use square brackets instead of moles per liter, or we can say M, capital M. So we're going to say concentration of the acid is equal to, now we're going to isolate the acid. So it's going to be all I did was I divided both sides by O2O. And that is now that is a classic titration problem. Frequently, you're looking at the concentration of an unknown acid. Now, lab 16, you calculate the unknown acid, which is vitamin C. Now, the problem with vitamin C, it's a triprotic acid, meaning 3 H's come off. So I keep telling them to not use vitamin C, but they continue to use it. Yeah. At neutralization, they're equal. Okay, if you go back up, right here, we have 1 mole of acid plus 1 mole of base equals 1 mole of water. So it's 1-to-1 only at neutralization though. Yeah, otherwise you're gonna have excess acid or excess base left over. It's gotta be 1-to-1. Yeah. No, I have to tell you what the acid is. Yeah. In fact, one of the questions on lab 16 is you have a diprotic acid. That means 2 H's come off. So that means you need twice as much base to neutralize the acid because there's 2 H's to neutralize. If it's, yeah. And then if you have vitamin C, it's got 3. And the problem with those, the first one comes off easily, the second one comes off not as easily, the last one doesn't come off much at all. So it's not a fair. It's really, and we're going to see in 1B that it gets quite complicated actually. And you end up having to solve a quadratic equation rather than a simple one here. It's just, you develop something called an ICE table. And the ice table generates a quadratic equation and you got to solve for that. And sometimes it's imaginary roots and but our class are having monoprotic strong acids. Easy. Okay. Now this is a classic titration program or problem. You've got unknown acid concentration and you put a known amount of volume-wise of the unknown acid into the bottom. Now for Saturday lab folks, that's what we're doing. Okay, we're putting a known amount of acid in. And we're going to calculate then the base concentration. It's kind of the opposite. And this is called standardizing your base. So what I've done is I pre-mix your base to be around 0.1 something. So one of the first steps is you take concentrated sodium hydroxide and dilute it down to approximately 0.1 something. I've already done that for you. I wanted to streamline it because that brings up some problems in the past. They don't mix it right. And anyway, so this is what we're doing in lab today. This calculation. Only we're using a dry acid in grams. So you're going to use the molar mass from the periodic table to calculate moles, because that concentration times liters only works if it's a liquid. Okay, any questions about this guy? All titration problems are basically the same, particularly if they're monoprotic acids. And in our class, they are. Just be forewarned, though, in your next class, they're going to throw a wrench in there and say, well, this is not monoprotic, it's diprotic. Diprotic means 2 hydrogens come off, or triprotic, 3 hydrogens come off. Okay, so that's your background in this. Are there any questions about titration? Now, at Sac City, they don't teach titration in their 2A class or their 300 class, which is like Chem A. I don't know. I've taught this equivalent class a lot, and we always do titration, except Sac City. On test 5, yeah. Now I'm going to go over the practice test on a separate video. So make sure you look at that. Yeah. Say again, louder. Yeah. Has anyone else tried it? Did it work?